It's two metaphysics that
It's his chance to go now.
Yeah.
Sorry, yeah. Okay, so I don't apologise for not having PowerPoint or a handout. It's a talk about structure of physics with no structure, but I will talk about physics. And at this point in the afternoon, maybe appropriate to start with some general comments and remarks about physics and metaphysics. And then what I want to do is advertise some questions that I think are of interest and a kind of conclusion which I'm tempted to draw from some different cases which I think might have something in common, but really I don't know how tight my argument is there, and a lot of it is at the level of kind of suggested remarks about which I'm still thinking. The reason for that is because I wanted to not just say the same thing I always say if someone says structure and physics, which is stuff about structural realism and ontic structural realism and particles and principle of identity of indiscernibles and so on. So I'm not going to talk about that, and hopefully won't say structure again, and definitely won't say structural realism. Okay, so well, look, I thought it would be appropriate to start by saying, well, what is metaphysics, and what's the relationship between physics and metaphysics, and kind of say some provocative things about, or maybe not provocative things, about them and their relationship. So it's common, I think, these days for people to say, and I think Jonathan says things like this, that there was this Quinean idiom in metaphysics, or Quinean approach to metaphysics, which was that metaphysics is about saying what there is, and that we've decided to go back to Aristotle, and or the new trend in metaphysics is not to talk about what there is, but what's fundamental. And that, of course, perhaps goes back to Aristotle. But I think there's a older, or a different characterization of metaphysics, maybe related, which is that metaphysics is concerned with reality as opposed to appearance. That, like, once we make the distinction between appearance and reality, then we're in the domain of metaphysics. And the job of metaphysics is to tell us about the reality beyond the appearances. And of course that was, the original pre-Socratic articulations that we think of a proto-metaphysics, of articulations of metaphysical theories, were precisely attempts to describe a reality that seemed very different from the appearances. So it doesn't seem like everything's made of water. But Thales says it is, and it doesn't seem like everything's made of little atoms, but Democritus said that it is. Now, on that conception then, you might think, right, well, physics just is metaphysics then, because what's physics? Well, it's the science that has revealed to us the reality beyond the appearances. Physics tells us precisely about those atoms that make up everything, and so on. So, on that conception, it seems like, and this is presupposing scientific realism, then it seems like what's left for metaphysics to do. Science tells us about the unobservable stuff, the reality behind the appearances. So physics either is metaphysics on this conception, or it's replaced it. Now let's try another characterization of metaphysics, again different from the one that contemporary philosophers talk about a lot, about metaphysics, about what's fundamental. Let's try, metaphysics is the attempt to say things, the most general things we can say. So what characterizes metaphysics now is its generality. And again you might think, well, that's just what physics actually is, right? Physics is the science that purports to be the most general bit of science. And the definition of fundamental physics, anyway, that we give in Everything Must Go, which is a book that advocates naturalized metaphysics, not the elimination of metaphysics, is that physics is the science that describes the world at all length and time scales, and is testable by measurements made anywhere and everywhere. So again, it seems like, well, that conception, you know, metaphysics is about what's most general. Again, you might think, well, we don't need metaphysics, we've got physics. Physics tells us is the most general kind of science. And then there's a third definition of metaphysics I want to offer you. It says, well, let's just define metaphysics by extension, right? So classically, metaphysicians talk about questions about the nature of space and time, the nature of matter, the nature of cause and law, and maybe identity and individuality. And then again, it seems like you can say, doesn't physics tell us about all those things? Doesn't physics tell us about the nature of space and time, the nature of matter? And hasn't physics told us about the nature of causation, that it's not like what we thought? I'll come back to that. Well, I'm saying all this really to advertise the positive conception of metaphysics that we have in Everything Must Go, which has the virtue of being a definition which makes metaphysics very clearly distinct from physics. And the definition, the characterization of metaphysics we give is really based on what Wilfrid Sellars says about what metaphysics is. But I think it's something that's been kind of underappreciated as, I mean, I think, you know, Everything Must Go is maybe a radical book which hasn't really been read very much, and so for that reason, or maybe, I don't know, but no one seems to have taken this up, and I just don't understand why. Sorry? Yes, exactly. Yes, quite. Well, the first half chapter was, of course, something that we never intended to write. It just sort of happened. But this characterization actually does appear right at the very beginning, and it's that metaphysics is the synthetic task, naturalized metaphysics, the synthetic task of saying what the world is like in virtue of the fact that we have all the sciences that we do. Right, so on this conception, metaphysics is about integrating the different parts of the scientific worldview into a single picture of the world. And that's not reducible to any particular science. You know, fundamental physics may be maximally general, and it may be about describing the world at all scales, but it has nothing to say about how there can be ontology at different levels, and how there can be emergent properties or anything like that. So if you think of like the job of saying what the world is like, such that we have the science that we have, as about integrating into a single worldview the fact that we have biology and economics and chemistry and fundamental physics, then it's not the task of any particular special science to do that. And arguably then there's a distinctive role for a metaphysician there. Now, I say that by way of advertisement, but now, since this conference is about metaphysical lessons from physics, and doesn't say anything about metaphysical lessons from the whole of science, then from now on I'm just going to confine myself to talking about things I think we can learn from physics on its own. And now I want to consider, well, no, let me start by some putative examples, and then I want to raise some skeptical problems and reasons why you might think this can't be done, and talk about some cases. So, when I was sort of growing up, I took it for granted that physics had taught us some very specific metaphysical lessons. So here are the things that I thought that physics, you know, it was a kind of common knowledge, right, that physics had taught us these things. Number one, no absolute simultaneity. Number two, space and time form a unity, form space-time. They're not really separate things, after all. Number three, there's no intrinsic direction to time. There may be an arrow in time, but there's no directedness to time itself. Number four, the world's indeterministic. Number five, roughly speaking, something like physicalism, right? That there's There's conservation of energy. Energy comes in different forms, can't be created or destroyed. All the different sciences treat of the same kind of energy. There's interconversion of heat and work, and physical and living systems and chemical bonds and all the other phenomena of the special sciences all have a physical basis. What number have we got to? I don't remember. Matter is not res extensa. Okay, matter is not fundamentally extended stuff in space. Solidity of the extended stuff we see around us, the matter that we see around us, is an emergent property. It's merely apparent. And there's no causation faster than light. Right, so when I was growing up, I think that those things were all, insofar as I have grown up, which is not wholly, those things were all just sort of like common, this is what we've learned, right? The scientific worldview has taught us these things. Now, to those lessons, I've got a whole list now of things that putatively have been added more recently, and some of them are things that I've tried to add myself, and some of them are things that people here have added to the list. So the first one is of the latter kind. There's no human supervenience is false. So I've argued this, but Tim Maudlin is well known for arguing that physics just shows us that human supervenience is false. Also, Tim argued that sameness of fundamental physical properties is path-dependent, and that sheds light on what kind of account we should have of objective resemblance, that we can't have theory of universals. Things I've argued, that there's relational individuation in physics, that things that lots of people have argued, that condensed matter is emergent. That goes back to what something I've already said. Something David's argued, that particles are emergent entities. Something that we argue in Everything Must Go, that physical entities are composed diachronically and dynamically, not synchronically. They arise because of the interactions among their parts over time. That has a consequence, we think, that existence is scale relative. Another thing I've argued, there might not be a fundamental or ultimate level. So Jonathan's got the fundamental level way up the top, and usually it's way down the bottom, so I call the top one the ultimate level and the bottom one the fundamental level, as everyone does, and I say it's an open question, but there's no particular reason to think there is one of either. And then more contentiously, lots of people think that physics has been telling us lately that there are multiverses, either for Wallacean reasons, or for string theory reasons, or for both, or other reasons. Okay, so it seems like then there's loads of metaphysical lessons that we've putatively learned from physics, right? But now let me mention three arguments that say, in fact, we haven't learned any of these things, and we can't indeed learn metaphysical lessons from physics at all. So the first argument is that metaphysics is underdetermined by physics. And so any attempt to arrive at metaphysical conclusions from physics involves some element of theory choice on sort of defeasible grounds, right? And I'll say some more about this as a skeptical argument. And the second argument, that we can't learn metaphysical lessons from physics, is simultaneously an argument against scientific realism. It's the argument from theory change. And then the third argument is the specific case of the interpretation of quantum mechanics, which seems to have thrown up skepticism, or it's thrown up the possibility that lots of the commonplace metaphysical lessons that I started with, we haven't in fact learned, that they're in fact open questions. And then I can think of a couple more Another reason you might think that we haven't learned, can't learn anything metaphysical, haven't learned any metaphysical lessons from physics is because, well, look at the state of quantum gravity, everything's to play for, people are, there's been such a failure to make progress that people will try relaxing pretty much any of the assumptions you can think of that they ordinarily have in order to make progress, and so everything's an open question. And another thought might be that, no, I'll leave it at that. Okay. So let me start with metaphysical underdetermination. So this term I get from Steve French, who's my PhD supervisor. I've learned an awful lot from him, though he's not to blame for me. He originally, in his paper, a great paper with Michael Redhead on the identity and individuality of quantum particles, they say right there, look, there's metaphysical underdetermination. If you want, you can believe that quantum particles are individuals, individuated by some transcendental feature, or you can believe they're not individuals because you don't believe in such transcendental features. I nearly said identity discernibles then. And it's the physics underdetermines the right answer. So, if you think of the task of interpreting physics the way that Van Fraassen does, when he says the job of the metaphysics of physics or the philosophy of physics is to say what the world could be like given that the theory is true, then this metaphysical underdetermination amounts to the fact that there's more than one way the world could be given that the theory is true. In general, more than one metaphysical picture is compatible with a given theory. Now, it's, you're probably all immediately thinking, yeah, but we know we've got underdetermination anyway, right? We have underdetermination of theory by data. And what do we do to break that underdetermination? Well, we appeal to theoretical virtues. And so we should do just the same thing in this case, right? To get our metaphysics from our physics, we'll appeal to the theoretical virtues of the different metaphysical pictures. And I want to say something about, in a bit, about why, in fact, let me just say something, I'll say something schematic about it and then I'll flesh it out with an example. Here's why you shouldn't be satisfied with that and you need to say more. I mean, just replace this one underdetermination problem with another. If you want to use the theoretical virtues to choose among different theories, you need to have a way of ranking those virtues, of weighting them. And no one's given such a way, right? And in fact, some of my colleagues in Bristol, Samira Kasha, and a couple of students, Kate Waterston and Kit Patrick, have done interesting work on an analogy between Arrow's theorem in theory of social choice and using theoretical virtues to solve the problem of underdetermination. And I kind of recommend that to you. So the idea is, like Gordon was talking about, how difficult it is to get people to agree about what counts as simple, right? But suppose you've done that, right? You've still got the problem of, okay, I've got a simple theory that coheres with background metaphysics, and that doesn't cohere with background metaphysics, and I've got a less simple theory that does cohere with background metaphysics. How on earth am I supposed to decide which is better? And in the history of science, actually, there are cases where it seems like it's not even true that empirical adequacy trumps the other theoretical virtues. So a good example would be Copernican astronomy, which was less empirically adequate than Tycho Brahe's theory, but widely thought to be a better theory, like as we rationally reconstruct it now. Right? So it's not even true that, like, first we decide, that the empirical virtues trump everything, and then we resort to the theoretical virtues, and now we've got a problem with the commensurability of different theoretical virtues, or even different versions of one theoretical virtue. It's like, yeah, we don't even know how to rank the theoretical virtues against the empirical ones. Copernican astronomy is no more empirically adequate than Ptolemaic astronomy at its mature stage of development as Copernicus found it. But Tycho Brahe's theory was more empirically adequate than both. And yet, on rational reconstruction, we kind of think, yeah, but you'd have been right to prefer Copernicus over Brahe, even back then, even not knowing what we know now. Even without Kepler's advance of having elliptical orbits. Okay, so, I mean, that might mean that, and this is one plausible thought, maybe it's really true that we can't learn positive metaphysical lessons from physics, but you might think, yeah, well, we can learn negative ones. We can learn that certain pictures of the world are impossible. So Bell's theorem being a classic example, Cauchy-Specker theorem, the recent PBR theorem, all these no-go theorems. It seems like they tell us that some particular combination of metaphysical assumptions is incompatible given the physics. And that might be true. Maybe we can learn only negative lessons. Even in those cases, it seems like, I want a slogan you might not expect to hear me say. Those of you who know me, what I normally say. I'm being open-minded here, right? So maybe even in these problem cases, in these cases, to really get metaphysics out, you have to put metaphysics in, right? And I think the case of Bell's theorem maybe exemplifies that for the kind of reason, sort of related to what I was saying to Janan, right? I mean, unless you put in the metaphysical assumption to the effect that the choices of what settings to put on the two wings of the EPR experiment are independent of each other, you don't have any problem with hidden variables or anything else. It's all no problem. In fact, I mean, if all you want is a model that recovers for you the occurrent actual phenomena, then there's no problem with EPR. Right? You just ascribe to the electrons the actual measured values that they end up giving. Right? The only problem comes when you want to have values that sustain counterfactual judgments about what would have happened if you'd measured something different. And we only have metaphysical grounds, really, for believing that the world has to be such that its states are independent of future decisions about what to measure. I mean, it's kind of metaphysical, it's a kind of modal realism is required there, right? If you're a complete modal anti-realist, if you just think all there is the actual stuff that happens, then you don't have a problem with having hidden variables. I mean, just ascribe to the properties, the values that they actually deliver. Ascribe to the particles the values that they actually deliver when you measure them. Okay, so that was like general problem. How can we learn metaphysical lessons given under determination? And I'm going to come back to like the concrete case because I mean Gordon said this morning about Ramsey saying, you know, he's kind of suspicious of all these people who tell you that you can learn this stuff but disagree with each other about what you learn. And we might similarly say, right, well, if I could really learn metaphysical lessons from physics by using theoretical virtues to choose among the different metaphysical packages that are underdetermined by the physics, then how come nobody agrees about, well, the case in question will be the interpretation of quantum mechanics. But let me just briefly mention the second skeptical argument. The problem of theory change is, if you like, it's supposed to be a problem about learning metaphysics from physics. It's a problem about learning ontological lessons. The person who runs the theory change argument isn't skeptical about science. They don't think there's no accumulation of knowledge. They don't think that science doesn't progress. They just think that over and above empirical adequacy, we can't, you know, we learn more and more about the phenomena, but we don't learn more and more about ontology. And the reason for that is because we've had really good theories in the past, and they've had one ontology, and then we've had a subsequent theory development that's abandoned the ontology. And I want to say, by the way, that I don't think the right way to make this argument defensible is to call it a pessimistic meta-reduction. And the pessimistic meta-reduction is as a crude argument along the lines of, you've always been wrong before, so you'll probably be wrong again. And that kind of argument was known to formulated by the Pyrrhonian skeptics, right? They pointed to examples, and just made people sort of suspend judgment by saying, look, you think you're really clever, but you think all those people in the past have done, but hey, they thought the same thing about their predecessors. But I think the right formulation of the argument from theory change is more nuanced than that, and it's weaker, right? And it's more specifically targeted against realism. So the right formulation of the theory change argument is that we've had cases of strong novel predictive success of physical theories where we've subsequently abandoned the ontology. And so there's no reason to believe, that we're not required to believe that novel empirical success has to be explained by being right about the ontology. So in a dialectical situation, this is an argument against someone who runs a no miracle argument, as opposed to just a general kind of skeptical argument like you were wrong in the past, you'll be wrong in the future. And I think this argument is important. It has to be taken seriously. We can think of lots of examples, and often people can find themselves to cases where there's abandonment of theoretical terms. And I think that's can be a bit misleading. So those cases are famously the ether and caloric, right? We no longer use those terms. Those terms are central in past theories that have novel predictive success. Have phlogiston as well. I have a paper arguing that actually phlogiston theory did have novel predictive success and phlogiston theory is often characterized as a bad scientific theory. It's not actually, it's quite a good scientific theory. So yeah, abandoned theoretical terms, we've got a problem, but actually we have a problem even when the theoretical terms haven't been abandoned. And my favourite example is atom. We kept the term atom. We completely changed our minds pretty much about what atoms were like. Atoms were supposed to be purely mechanical entities that were indivisible. And we know for sure atoms are not purely mechanical entities, they're not indivisible. So it can be a bit misleading, like whether or not we have continuity of a term doesn't really tell us whether we've got discontinuity in our ontological claims. Other examples would be space and time, mass, right? And you've changed our minds radically about the real ontology of space and time, the real ontology of mass. We happen to use the same terms. I think it's completely arbitrary, actually, that we really, there's more reason to call the electromagnetic field the ether than there is to call atoms atoms. It just seems to be a bit of an accident of history that we abandoned the term ether, but we kept the term atom. Okay, so, and then let's just take the specific case of the interpretation of quantum mechanics and see how it seems to undermine the learning of all those metaphysical lessons I started with. Right? So the problem is that the competing interpretations turn out to put everything becomes questionable, right? So is the world really indeterministic? Well, no, not according to Everett, and not according to Bohm theory. Is there really relativity of simultaneity? Well, not according to those people who think that that really is a trade-off between special relativity and quantum mechanics, and the advantages of Bohm theory, even if it required us to have to return to absolute time, that would be a price worth paying. And of course, it might be that in cosmology we get back to some notion of an absolute time. Are there really particle trajectories? Again, up for debate. There's an interpretation of quantum mechanics where there's retrocausality. So it seems like everything's up for grabs given all these different interpretations, and so many years of debate have led to no consensus at all about how to use theoretical virtues to choose among those theories. And actually those debates seem to perfectly illustrate the abstract problem of how can we use theoretical virtues, because people can't agree about which is simpler, right? So usually people say, I can't believe in Everett because it's so ontologically, it's so unparsimonious, right? But the Everettians say, no, you've got that completely wrong, right? Actually, Everett is more parsimonious than the rivals. And why? Well, because it doesn't require an ideological distinction between the possible and the actual as things unfold, because it doesn't require collapse, because quantitative parsimony is not a theoretical virtue, whereas and it's qualitatively parsimonious, blah, blah, blah. Is bone theory. Okay, so I think, and again, right, people say, oh, not being ad hoc is a theoretical virtue, but then there's no agreement about whether bone theory is really ad hoc or not. Like some people say, yes, it is definitely, and bone will jump up and down and say, if not, because we have the right understanding of ad hocness, we'll see that it's completely contingent, that it could have had that empirical success and didn't. So really, it seems like, if it was really true that we solved the problem of metaphysical undetermination by fields of theoretical virtues, then we ought to have been able to solve it, but we haven't been able to. And I'm always struck by the fact that over here, I remember last time I was here, I got stuck because of the ash cloud and that was over Iceland. And as a happy consequence, I got to come to an extra event at Rutgers where David Albert was giving a talk to the students about quantum mechanics. And kind of more or less said, okay, there's two ways you can think about quantum mechanics. There's GRW and there's bone, right? But if you go to Oxford, it's more or less like there's Everett, and maybe some people might take seriously kind of neo-Copenhagen type quantum information versions of quantum mechanics, and not take terribly seriously bone and GRW. So, what's going on? Have these people failed to absorb like the literature on theoretical virtues and so on? No, it's actually just that that literature isn't determining what we should think, and so we're not solving the determination problem. Okay, so all very skeptical. Okay, so all of that notwithstanding, I'm just sort of saying all that because it seems to me those are genuine problems, and I don't have an answer to them. I don't have a particular agenda. In fact, my agenda is probably the opposite of like what the tone of what I've just been saying. But they're things I think we should talk about and think about. But in any case, I now want to try and give you an example of a lesson that we shouldn't learn from quantum mechanics, and propose a lesson that we should learn. So that's what I'm going to do. How much time do I have?
You get about 20 minutes.
I've got about 20 minutes?
Yeah.
Okay.
A little longer.
Those are my preliminary remarks, so on to the paper. Okay. So there's lots more to say, by the way, about the relationship between metaphysics and physics, and one recurrent theme in that debate is, well, how exactly do we draw the distinction between metaphysics and physics? There's no metaphysics-free version of quantum mechanics, you might think. There's no interpretation-free formalism that actually counts as physics and not just mathematics. Really interesting questions there, which I'll skip over, and I'll just get on to the lesson that I think we shouldn't learn. Okay, I'll start with that. And the lesson I think we shouldn't learn is the lesson that's often what people have in mind when they say quantum mechanics is non-local. And I'm sort of disappointed that David Albert, I'm extra disappointed that David Albert isn't here, because I want to take issue with the way that he presents this lesson in a Scientific American article. And I think what he says there is wrong and misleading. And I want to say why I think that is. Okay. So, non-locality is a crude term. If we think about the history of physics, another term that often gets used is action at a distance. And I think if we ask the question, is quantum mechanics non-local? Then, because non-local is a crude term, the answer is yes and no. But I think if we ask the question, is there action at a distance in quantum mechanics? The answer is no. Okay. So I want to explain why. And I want to explain why what David says I think is misleading about this. So David gives this analogy in his Scientific American article. And I think, look, fair enough, you could say, well, it's a popular article, and he's just brushing over some distinctions that you might make in a more academic setting and so on. Okay, fair enough, but nonetheless, you do kind of. I think it's important. So in this article, he says, yeah, quantum mechanics is not. He wants to establish that quantum mechanics is incompatible with special relativity, and this is a strong claim to make. It's like saying there's this fundamental schism in physics. We've got these two fundamental pillars of physics that are incompatible with each other. And it's often said that quantum mechanics is incompatible with general relativity, perhaps by physicists. But if you ask most physicists what are the two pillars of the Standard Model, and the Standard Model is like the state of the art of physics, right? It's the most empirically adequate theory we have of physics, then they'll say quantum theory and special relativity. Right? And hard to see how those two pillars could be incompatible with each other, right? If they're supposed to both be pillars of the Standard Model. And I think it's kind of failure to be really specific about what's meant by non-locality that allows people to say that quantum mechanics and special relativity are incompatible. So David says, we're talking about EPR style case. It's as if, and I can't remember the exact places he says, but it's something like, Vermont and Indiana or something, right? It's as if someone throws a punch in Vermont and someone in Indiana gets a black eye, right? So why isn't it like that? Okay, well, number one, because black eyes and punches are the kinds of things that only come one way around in causal processes, right? There's punches cause black eyes don't cause punches to be thrown, right? Disanalogy, right? With EPR phenomena, right? Number two, you can punch someone and give them a black eye, even if well, in the example he considers, like the black eyes in Vermont, the punch in Indiana, or whichever way around it was, he never mentions, but that would only happen if the black eye, or the eye, and the fist were prepared together in a common state, like somewhere else, and then separated later. Right? But that is a really important feature of quantum entanglement. Right? You can't do anything to any old particle over there by doing something to a particle here. No way. You have to have a common source, and then they separate. They have to be prepared together. More generally, when people start to talk about quantum mechanics being non-local, there are a couple of things, and it being incompatible with special relativity. There are a couple of things that they don't mention, but I think they should. So if we're going to have a balanced picture of the kind of non-locality that there is in quantum mechanics, and the extent to which it's in tension with relativity, we also need to, as well as drawing attention to the ways in which it's non-local, we also need to be really clear about the ways in which it's not, or the ways in which it's compatible, right? So let me just mention, like two. Okay, so David, nowhere in this article on how quantum mechanics is incompatible with special relativity mentions the Dirac equation. Right? But what's the Dirac equation? Well, it's the relativistic wave equation of the electron. Right? And it's empirically adequate. In fact, in order to explain why gold is gold, you have to use the Dirac equation, not the Schrödinger equation. So it's kind of worth mentioning, isn't it, that there's this empirically adequate theory that you get by conjoining special relativity and quantum mechanics in the form of the Dirac theory of the electron, if you're going to make the case that quantum mechanics is incompatible with special relativity. Number two, well, I've already mentioned Lorentz covariance as a heuristic principle being imposed on interactions is a fundamental successful heuristic in the development of quantum field theories. All quantum field theories obey the principle of local causality that says that space-like separated operators have to commute. So, again, strange to talk about the incompatibility of quantum mechanics and special relativity and not mention that fact. And then the third thing I want to say, which I just think that this is interesting and it's not usually mentioned when people are talking about quantum mechanics and non-locality. It seems to be important. See, if we think back to a discussion about action at distance in the history of physics, Newton says famously this line about how it's inconceivable that something here can affect something there without something in between, happening in between, right? And there the concern is not so much with the speed of the interaction between them, which we're accustomed to thinking is the important thing because of special relativity and so on. It's just the mere idea that this thing could affect that thing without something happening in between the two, right? And I don't know how important this is, but it's no one ever mentions this, and I thought about it and I thought, hey, no, that's really interesting, right? So you've probably all seen this equation. The rho there is the probability density, and that thing changing over time plus this quantity, which is called the probability current, equals 0. Now, what does this mean? Well, if you integrate this and you take this probability density to be given by mod psi squared, then you get this equation. Oh, and we're considering some volume. Right, there we go. And I have to use, so I've got some volume, V, with a boundary S. And I'm using the divergence theorem and integrating. And what this basically tells you is, suppose I've got a region over here. Well, basically what it's telling you is that just take a single region. It's telling you the probability density can't change without probability current flowing out of the boundary. Right? But now, let's think about the case of two spatially separated regions and think about the probability density of the wave function of a particle in those two regions. And suppose that over time, the probability of the particle being here goes down and the probability of here goes up. And this tells you the only way that to happen is if probability flows between the two regions. So, interestingly, this equation is exactly the same equation that you get in hydrodynamics and electromagnetism. And hydrodynamics was the sort of founding theory in field theory, which was developed precisely to solve the problem of locality of processes in different parts of space. And so the overall lesson of this seems to me to be, well, there's a really important sense in which quantum mechanics is is obeying a kind of locality. Okay, so that's that. And now I just want to turn to like why the EPR correlations shouldn't be thought of as the causal. Thank you. So negative lesson. I say we shouldn't draw the lesson that quantum mechanics is non-local. That's too crude. What lesson should we draw instead? Well, this is a familiar point, really. Well, we should draw the lesson that physics has told us that there's a new kind of ontological dependence between spatially separated things that isn't causal dependence. So, in other words, it's a familiar point that there's some kind of there's some kind of category of non-separability or something like that. And given that I've like almost completely run out of time, I was going to give 3 examples. So I'll try and cut to the chase. Okay. So what we have, in the EPR case is we've got this correlation between A and B. We've got this probabilistic structure that the probability of A given B is greater than the probability of A on its own. And when we see that kind of thing, we think, oh, well, maybe B causes A. But we also see that the probability of B given A is greater than the probability of B on its own. And when we see that kind of thing, then we think, all right, well, maybe there's some third thing, C, such that the probability of A given B and C is just the same as the probability of A given C. And likewise for the probability of B given C and A. And so we think that the natural thing that the standard theory of probabilistic causation would tell you in this situation is either there's a direct causal link between the two, or there's a common cause producing both. But we know from Bell's theorem that at least if we think that the common cause has to lead to factorizability of the probability distribution, that there is no common cause of structure here. So what about the idea that A causes B? Well, it would be fine to think that, were it not for the following kind of considerations that tell against thinking that there's a direct causal link. So those considerations are that, one, that really there's nothing whatsoever to break the symmetry between A and B in the case where the measurement events that we're talking about are space-like separated from each other. So there's the source, and here's measurement event A, and here's measurement event B, and now we know from special relativity, well, there's no unique time order to A and B. There's absolutely no reason to think that A causes B rather than B causes A. And so that's one thought. The second thought is, if this was causation, it would be utterly unlike any kind of causal interaction that we've ever seen before. Well, why? Well, one, because all the causal interactions we know about are mediated by one or more of the forces that we know about, but this isn't. Two, all the causal interactions we know about, all the forces that we know about, there's some kind of effect of some kind of diminishing of the causal power as you get further away. But nothing like that holds in this case. It's not like any other kind of interaction. It's completely unaffected by, as someone was saying before, Jonathan was saying, by how far apart the particles are. And finally, the thing I think is really important is that when we have action at a distance, there's the I in its state. It's got a definite state. And then the fist, which acts, throws, the punch is thrown on the other side of the world, and the I in the analogy changes its state. So all we have in that example, and in the paradigmatic case of action at a distance, is there's an element of reality that has a determinate value, and it changes. But independently of some interpretation of quantum mechanics to the contrary, I mean, just prima facie, the way that quantum mechanics is described, there is no such change in an element of reality. Right? The measurement result on the left isn't a change as such. Right? There isn't a spin in the x direction prior to you measuring the spin in the x direction on the left, or to be changed by the measurement event on the right, or vice versa. Right, so for all those reasons, I think the right thing to think, and this is a standard view, is that, and I'm just I know, reiterating it because it seemed like it's in, I don't know, I wanted someone to tell me what's wrong with it, if there's anything wrong with it. But maybe you all just think, yeah, that's right, that's the standard view, it's non-separable, it's not non-local. It's passionate dissonance, not actionate dissonance, whatever you want to say, right? But now, suppose we've got that category of, so then the claim is, right, so there's a lesson. The lesson is, we need this extra category. We have no reason to posit it classically, but in quantum mechanics we have a reason to posit it. And the other thing that I was going to do was say, well, I think in a different way, we get the motivation to have a similar third category of a kind of ontological or modal dependence between outcomes, between states, that isn't causal dependence from two other cases. And the two cases which, so I'm kind of not sure about this, right? These cases differ quite a lot from the EPR case. Is that a bad thing or a good thing? I mean, you could say, well, no, it's a good thing because that shows that you've got sort of several independent kinds of phenomena pointing you to this extra category that you need. Or you might say, no, there's no reason to believe there's a single category here. You've got more than one. Okay, so what are those two cases? Well, one is the A-B effect, and one is the occurrence of weak values in quantum mechanics. So, without going into loads of detail, so why do I think these cases are similar? Well, in the A-B effect, you have an interference experiment, and you have a solenoid in the middle, and you have a non-zero field, electromagnetic field, inside the solenoid, but the electrons in the interference that are interfering with each other, or there's a single electron maybe over time producing an interference pattern in the familiar way, never get anywhere near the field inside the solenoid. And the field is zero, idealized to be zero outside the solenoid. And so, again, it looks like some kind of non-locality. But again, we have no manifest contradiction with special relativity. Because in the A-B effect, if I make the solenoid spatially distant, so my electrons are taking paths that are going a long way away from the solenoid, and then halfway through the experiment I turn the solenoid on, the shift in the interference pattern will propagate at the speed of light from the solenoid to the paths the electrons are taking. Right? So I can't signal by changing the interference pattern due to turning the field on in the solenoid faster than light. And I gather this has been done, and that someone's done an experiment where they tried to make sure they set things up in such a way that you could see whether or not the turning on of the solenoid was happening instantaneously in the frame from which you're looking at the whole situation. And no, sure enough, no, it propagates at light speed. Right? And now, again, there's a kind of metaphysical underdetermination with the A-B effect, because you could say, well, nonetheless, the field inside the solenoid is non-locally affecting the electrons. But you can also say, no, actually there's something that's locally affecting the electrons, and that thing is the electromagnetic potential, which we didn't think was real, but now we do think is real because we posit it as the reason, the local reason why the electrons behave as they do. But if you say that, then, which I think would be the better thing to say, given the fact that I just mentioned that you won't, the turning on the solenoid will take time to have an effect on the electrons. If you think that, then the electromagnetic potential at a point isn't what determines the shift in the interference pattern. The phase invariant, the gauge invariant expression for the shift in the interference pattern depends on integrating around the whole path, and so it seems to be a kind of non-causal dependence of the state of the electrons on the whole properties of this path all the way around. Now, the case of weak values, I probably haven't got time to say anything very much about, because what I thought I was going to do was say everything I've said, and then briefly explain what weak values are, because I guess, who knows what weak values are? A few of you do. So I was kind of like, I'm tempted to say about weak values that since a causal interpretation of them would have the future causing something in the past, that's a good reason to think it's some kind of non-separable ontological dependence of the future on the past rather than causal dependence. So that's like roughly what I was going to say. But I think I haven't got time to say that, and I've probably said enough to provoke lay people. So probably appropriate to stop. Thanks.
Okay, we're going to have another. We'll get into the question and answer session. Sorry, are you guys prepared to have your conversation loudly?
Yeah.
Okay. So the announcement is that we're going to, after the talk concludes at 7 o'clock, we're going to meet at Makeda's for dinner. Obviously, there's not going to be funding for everybody's dinner, but if you want to come along and buy yourself some food at Makeda's, you can sit around us and talk.
There'll be a group leaving from the hotel at from the Hilton Hotel at 6:30. If you don't know how to get to Makeda's, get with a local or go to the Hilton Hotel at 6:30.
The Hyatt.
Hyatt.
Yeah. Do we have a Hilton?
No.
How classy are we in New York? Okay. So when last we talked, James said that he would share his own question.
Yeah, yeah.
So I will sit down and let him take the floor.
Yeah, well, then I have to take Barry. I don't really want to.
So I think two related matters. One is, I think you took this punch black eye metaphor a little too seriously. Of course, in some ways, the relationship is like causation. In some ways, it's not. You pointed out some ways it's not. But one way in which it is, which you didn't mention in this, that is that the counterfactual, that if you hadn't have punched the guy, you wouldn't have had a black eye holds. And it's parallel counterfactual. Now this counterfactual holds in the quantum mechanical case. If you hadn't made such and such a measurement which had such and such an outcome, then the measurement that you made of the other
Right.
the other way wouldn't have had such and such.
I didn't actually mention any ways in which they're analogous, actually. No.
Right.
I only mentioned the ways in which they're not.
Right, so I think the
But
idea,
I
I don't
don't
want to
agree.
really make it my job to defend David here, but I think this was, a sort of throw one into the
But I don't agree that the counterfactual holds. Right. I mean, it's not obvious that it does. So it's not even obvious that the counterfactual, the trivial counterfactual, under indeterminism. Right, so suppose I measure x spin on the left, and I get up, right? It's not even obvious to me that the subjunctive, if I were to have measured x spin on the left, I would have got up holds. Right? Because the whole point about indeterminism is I could rerun the world in exactly the same way and get a different outcome on that. right? So what's that? You know, the usual condition on there's a sort of facticity condition on counterfactuals, right? That if it holds in the actual world, it holds counterfactually, right? But I don't think that's right. So I certainly don't agree that the counterfactual that there's anything counterfactually true, right? So if I were to have measured something different on the right, I might have got something different on the left, because that's a different world.
When you say the settings are the same on both sides,
Yeah.
and you back it up over here and down over here. If you had got down over here, you would have got up over here. Is that good enough?
Yeah, that's true. But that's not analogous to black eye and the punch case, right? Because that's like saying if he were to have got a black eye. I mean, where's the symmetry, right? I mean, in the black eye punch case, it's only true that if you threw the punch, he would get the black eye. But it's not true that if he were to have got the black eye, you would have thrown the punch, but someone else could have thrown the punch.
Like you said, they're disanalogous.
Right, but I suppose what I'm saying is they're so disanalogous as for the metaphor to be completely misleading. Right, I mean, what?
Yeah.
You can say, okay,
anyway,
what's the point of the metaphor? Right, what's supposed to be analogous? That there's a counterfactual dependence. But I mean, there is some kind of modal dependence, right? But that's exactly my point, right? I mean, my point is that we need a category here to cover the fact that there's an ontological dependence between the outcomes, but no causal dependence.
I don't think anyone's going to disagree with that, and that one's understanding whether it's going to depend on interpretive quantum mechanics. I mean,
Right.
without an interpretation of quantum mechanics, you kind of have to see what to say here, which is the related point, and that's that the conflict between relativity, special relativity, and quantum mechanics isn't a conflict in what they would predict, or that there aren't ways of combining relativity and quantum mechanics.
Right.
It's that, well,